For part 2 of chapter 3, we'll continue looking at atmospheric temperatures, specifically seasonal lag and extreme temperatures, the vertical distribution of temperature, a first look at net energy budgets, and the horizontal temperature distribution. Seasonal lag. There's about 1 month lag between the maximum solar input, the summer solstice, and the maximum temperature. In short, it takes some time to warm up or cool down. There's some thermal inertia there. So over land surfaces, here we're looking at Charleston, South Carolina, Illinois, Italy, Russia, Canada. The maximum solar input is all going to happen in these northern hemisphere locations during the summer solstice. However, the warmest month is actually about 1 month later than that, with the exception of Naples, Italy, which is more like 2 months. Looking at the winter solstice, that's going to be the time of minimum solar input, and the coldest month actually happens again about a month later due to the thermal inertia in the system. So why is it that Naples, Italy has an extra month of lag? Well, it's simply surrounded by a lot of water. It takes even longer for water to heat up or cool down, so therefore the lag is extended. Here we're looking at the vertical and meridional temperature distribution. Vertical, obviously we're going upward in height here on the y-axis, and then meridional means simply looking from the equator towards the poles. The first thing to note, here's the summertime vertical meridional cross-section. In July here, the average lapse rate on a broad brush average is about 6.5 degrees Celsius per kilometer, and that varies substantially between day, night, different parts of the globe as well. The second thing to look at is that the largest north to south temperature gradient occurs in the winter. That's because the poles cool so effectively during the winter, you get a stronger temperature gradient across there. We'll find that this temperature gradient actually helps promote a strong pressure gradient aloft, which helps support a strong jet during the winter. Tropopause is also higher in the tropics than it is near the poles. The reason for this is because thunderstorms mix up the troposphere here up to higher heights around the equator, driving the part of the atmosphere that turns over, otherwise known as the troposphere, higher and higher. In the poles, the cold air compresses that tropopause rate down. Air is a little more stable down this location. Last thing to look at is because the average lapse rate is about 6.5 degrees Celsius per kilometer in the troposphere, and because the troposphere is tallest over the tropics, that means there's a large chance for temperatures to drop as you go up very high towards the tropical tropopause. That means that just beneath the tropical tropopause are the coldest tropospheric temperatures. This graph considers overall average temperatures at sea level and at some arbitrary higher location on a mountain. Obviously, sea level is going to be a little bit warmer than the mountain just because of the altitude effect. The biggest component here, though, is looking at the change in the temperature over the course of a day in sea level versus mountain. And really what you'll find is that the biggest change, there's not a whole lot of difference during the time of maximum heat in the afternoon. However, the largest difference occurs overnight, where the mountain area cools much more effectively. Why is that? Because the air is less dense at high altitude, which means it has less greenhouse gases. That ultimately means that it can trap less heat at night, allowing it to cool more effectively. We're going to take a first look at the net radiation budget in this chapter, and then we'll revisit it towards the end of the class. Net radiation depends on the gains and losses of shortwave solar and long-wave radiation. Here shown is the budget: shortwave incoming, coming in from the sun, shortwave leaving the surface, that would be what is reflected, and then infrared radiation coming down from the sky, mostly from greenhouse gases and clouds, and infrared radiation leaving the surface. Anything leaving the surface has a negative in front of it, and anything coming down to the surface is a positive number. I've written it a different way here just to show that the shortwave budget, nothing on the Earth emits shortwave, so you're really just considering what's the total amount coming in from the sun, the direct beam plus what's scattered, times what percentage of that or what fraction of that is actually absorbed. So again, this component of shortwave leaving is really what's just getting reflected off the surface. You can have an excess or a deficit of net radiation. These animations are showing net shortwave radiation, shortwave coming in minus shortwave leaving, and you can see there's a periodic oscillation that follows the sun. This lower left one's looking at long wave radiation, and this is again how much is coming in versus how much is leaving the surface. Since the surface in general is warmer than the overlying atmosphere, these numbers are negative because you're losing more energy from infrared radiation than you're gaining coming back down from the sky. Now, net radiation is the sum of the net shortwave radiation plus the net longwave radiation. You can see instantly that the net radiation looks more closely like the shortwave radiation, so that's what's forcing it the most. However, the long-wave radiation is important as well, and it does produce a lot of differences along each latitudinal band. Anytime you have an excess of radiative energy at the surface, say during the heat of the afternoon, there's four things that could happen to it. The first is it could just evaporate liquid or sublimate solid ice, and that's called the latent energy component, LE. It also could conduct energy into the ground, so it could heat the surface, and then the surface gets hot. If the surface is hotter than the deeper ground underneath it, by a process of conduction, you can move heat towards the deeper ground. You can conduct or convect energy into the air, meaning that a hot surface that's absorbing radiation could give some of that energy by conduction to the overlying air, which will then convect upwards, moving the heat even further into the atmosphere. The fourth thing that you could have happen is just simply raising the temperature of the surface over time, so the change in temperature of the surface over time. Here's just looking at two of those components and how they look globally. Here's the sensible heat flux, with blues meaning heat's going from the air to the surface, reds meaning that heat's going from the surface to the air. The largest magnitudes here are found when the vertical temperature gradient is largest. For instance, if you have hot land or a hot ocean underneath cold air, there's going to be a large sensible heat flux going upwards from hot to cold. Let's look at here. We do have times in the summer. Let's wait for summer to come back here in the northern hemisphere, and we see there's a large sensible heat flux in the northern hemisphere over those hot surfaces. On the other hand, during the winter time in the northern hemisphere, we see there's actually sensible heat flux going the other way. The air in the atmosphere is warmer than the surface at times in the winter, and that pushes heat to the surface. The other thing that's interesting here, in the winter time in the northern hemisphere, you can clearly see that the Gulf Stream, which is a warm current along the east coast of the United States, is giving a whole lot of sensible heat to the overlying atmosphere, especially during the winter when the atmosphere is cold. The latent heat component here, you can also see there's a lot of evaporation that occurs off that same Gulf Stream off the east coast of the US. And you can also see there's a whole lot of latent heat flux over areas like rainforest in the Congo and Amazon area because there's a lot of water to evaporate. The reds here are showing evaporation and vertical transport of water vapor, and the blues are showing condensation. The factors that most influence the horizontal distribution of temperature are 1. The latitude. The tropics are warmer than the poles due to sun angles. 2. The surface properties. How much moisture you have, what kind of soil. 3. The proximity to warm and cold ocean currents. It's hard to change the temperature of the ocean substantially, even with a lot of energy. Therefore, if you live close to them, your temperatures won't fluctuate as much as other places that are more continental. You also have to look at elevation, the aspect, and the topography as well. Here's a latitude example. Record temperatures are actually found right at 23.5 degrees north. 9 of the top 10 record temperatures are found there, and one of them is at about 23 degrees south in Australia. They're not found at the equator. Why are they found so far north and south and not at the equator? Well, because the solar declination spends only about 30 consecutive days during the equinoxes crossing the equator from about 6 north to 6 south, but instead it slows down and turns around as it approaches 23.5 degrees north or south, which means it spends about 85 days consecutively during the solstice periods hanging around from 17 to 24 degrees north or south. This allows for heat to build up over a 3-month period, which greatly warms the region during their respective summers. There's also mostly clear skies at these locations, and this is mostly a dynamic effect from what's called the descending branch of the Hadley cell that we'll explore in Chapter 5. In the deep tropics, instead of having a dry area with descending air, you instead have rising air, converging air from the trade winds, and mostly cloudy skies and thunderstorms, which helps cool it a little bit. The third thing, why these temperature records are at 23 degrees north and south, is the large sensible heat flux from the surface goes to the air in these deserts because this loosely packed sand really can't conduct much of that energy downwards into the deep ground, so its only option is to give it to the overlying air because there's also no water to evaporate. Surface properties. You have to consider the moistness of the surface. How much energy will just evaporate water versus how much goes to sensible heating of the air. If you don't have water to evaporate on your surface, then a lot more sensible heating could be expected. You have to consider the reflectivity, or the albedo, how much of the radiation actually gets absorbed versus how much is reflected. You have to consider the material that is actually being heated, how much energy is being conducted into the ground. Is it loosely packed sand with low thermal conductivity, or is it a rock that has pretty high thermal conductivity? And what is the heat capacity? How much energy does it take to change the temperature of that, which is a property of the material and also the density of the material too. Here we're going to go through a little example showing why the oceans are so hard to warm up and they're so reluctant to cool down. In other words, why do they have such high heat capacity and why do they have such high thermal inertia, reluctance to change its temperature? This graph compares San Francisco, which has high thermal inertia because it's close and downwind from the ocean, a maritime climate, versus Norfolk, Virginia, which actually is a continental climate because what's upwind of them is a continent. Even though they're on the ocean, they're more continental because of the way the wind pattern goes from west to east. What's shown here is that the maritime climate of San Francisco, the green line here, does not have as much of an annual range of temperature as Norfolk does. Norfolk has a warmer summer and a colder winter, and that's the continental influence that's upstream of them. So why exactly is it so much harder to warm the ocean surface than the land surface? Well, the first thing you have to consider is specific heat capacity, which is the sensible heat required to raise the temperature of a gram of a substance by 1 degree Celsius, not considering any phase changes. It turns out liquid water has a higher specific heat capacity than almost any other substance. Thermal inertia is partly due to the specific heat capacity of soil versus water. So liquid water, it takes about 1 calorie of energy to raise a gram of the water 1 degree Celsius. For moist soil, it takes 1 calorie of energy, the same amount of energy, to raise 1 gram of that soil by 4 degrees Celsius. So it's easier to raise the temperature of the moist soil than it is of the water. You also have to consider, though, beyond the specific heat capacity, which is a property of the material, well, how much material do you have? What is the density of that material? So you have to multiply this by the respective densities of a cubic meter of soil, about 2,000 kilograms, and a cubic meter of seawater, about 1,000 kilograms. So you take the water, you multiply the specific heat capacity times the density, and you get a total heat capacity here expressed in how much energy does it take to warm 1 cubic meter of water by 1 degree Celsius. For moist soil, you take the specific heat capacity of it, which was 1/4 the amount of the specific heat capacity for water, multiply it times its density, which is twice as dense as water, and now you get 500 kilocalories required to raise the temperature of 1 cubic meter by 1 degree Celsius. The last thing you have to consider, which is really the most important, is what depth of the column gets heated in water versus land. And it turns out, over land, so all that heat gets accumulated in a very shallow portion, we could just talk about maybe perhaps 1 meter deep, because we also have to consider not just radiative heat coming from the sun, but also sensible heat that's arriving from the atmosphere. So we'll use a ballpark of 1 meter. Using that 1 meter depth, times our density and our specific heat capacity, we come up with a land heat capacity per square meter at the surface of 500 kilocalories per meter squared per Kelvin. For the ocean, the sun penetrates between 10 and 200 meters depth, depending on what's in the water and how clear it is, and the atmosphere warms a very thin layer at the surface. However, there's always waves and wind that are mixing up the ocean surface layer down to about 60 meters deep, which is called the mixed layer. So if you use a ballpark average of about 60 meters, all this energy is getting mixed in the ocean, and multiply it times our first calculation for how much energy does it take to warm up a cubic meter of ocean, you get 60 times the original calculation, which was 1,000, and now you get 60,000 kilocalories are required to warm up 1 square meter of ocean at the surface, and this is because a lot of that energy is lost to deeper levels underneath, and it's really the surface we're worried about when we're talking about the atmosphere, because the surface is the part that communicates with the atmosphere. So in total, these calculations show that the ocean's surface area has about 100 times more thermal inertia than land surface area does, so it's a substantial difference. And this really shows why it's so hard to warm up the oceans, especially during one day-to-night cycle The oceans are really not going to be affected much by the energy budget that's happening over that time, and we're showing hardly any change from day to night over these oceans as a result. Another thing you have to consider is the proximity to warm and cold ocean currents. A good example of that is that the warm Gulf Stream that goes along the coast of the United States here on the East Coast, that brings up very warm water from the tropics towards the poles. At the same time, there's prevailing westerly winds going from west to east, which advects or moves some of that heat towards England, and England will actually see about 20 degrees Fahrenheit warmer temperatures on annual average than similar latitudes that are not downstream of the Gulf Stream air. The last thing to think about is the aspect in topography. Being on the north versus south side of mountains has a large effect on the local climate due to the shading involved. We live in an area with a huge effect from the mountains, not just this shading effect, but also where we are in Boulder with the mountains to our west. With west winds, we tend to get downsloping winds that compress and warm as they come down the slope, leaving us with warm, dry, and windy conditions with a west wind. With east winds, however, you get an upslope condition where the air is coming up from the east, up the mountains to the west, and that cools the air. And if it cools the air enough and the air has enough moisture, it'll condense into clouds and maybe cause snow and rain. The tornadic storms and severe storms in the Great Plains would likely not happen if an east to west mountain chain existed there, because without a mountain chain there on the flat plains, you have nice dry cold air from Canada clashing with warm moist air from the Gulf of Mexico, and severe storms can really develop where these air masses collide, otherwise known as frontal zones. The last thing to consider is what's driving the atmospheric motions is that there's an excess of radiation at the tropics and a deficit towards the poles, so therefore there's heat transfer processes by the movement of moisture and by the movement of heat. What this means is that there's motion in the atmosphere, and so the energy budget of a location upwind of you could affect your climate as well if the prevailing winds are always blowing that area's conditions towards your location. This is a process known as horizontal temperature advection when you're talking about the transfer of heat by the horizontal flow of a fluid. Chapter 3 had a number of key points. First, from the last lecture, seasons result from the tilt of the Earth with respect to its orbital plane. The annual temperature range is largest over the mid-latitude land areas due to large seasonal changes in that sun angle and the length of day there. Those land surfaces will warm and cool faster than the oceans, and also the seasonal snow cover. Diurnal temperature ranges, otherwise known as day to night temperature ranges, are really a function of the wind speeds. The lower the wind speed, the more you can effectively cool off overnight, increasing your diurnal temperature range. The humidity is a big player here. More humidity in the system generally will reduce your diurnal temperature range. Of course, the length of the day versus night is important. The heat capacity and the soil conductivity, properties of the material that's being heated at the surface, and also the latitude or the sun angle. Key points from this recording, part 2 of chapter 3, there's a seasonal temperature lag, about a 1-month period between the maximum solar input, the summer solstice in the northern hemisphere, and the maximum temperatures. It's about a month over land surfaces, but much longer as you get closer to the ocean, because the oceans have high thermal inertia. Vertical variations in temperature. The tropopause, which marks the top of the troposphere, is higher in the tropics than the poles. On average, the temperature decreases, on broad brush average, 6.5 degrees Celsius per kilometer as you go up in the troposphere. The tropospheric temperatures are coldest just below the tropical tropopause. Surface energy budgets involve net radiation budgets, which consider how much short waves arriving versus leaving, and also how much long waves coming in versus leaving. And the net radiation can have an excess or a deficit. If you have an excess of net radiation, there's a bunch of things that could happen to it. It could go into sensible heating, it could go into evaporating water, or it could conduct energy to the ground, or it could simply raise the temperature of the surface over time. Horizontal variations in temperature are mostly a function of the latitude, the tropics are warmer than the poles, the surface properties, how much moisture to evaporate, what's the thermal conductivity and soil type, proximity to warm and cold ocean currents. Again, the oceans have a high thermal inertia, so if you live by them, you also have a high thermal inertia. Elevation aspect and topography is important as well. As you go up in elevation, you cool more effectively at night due to having less greenhouse gases, so your night times are typically colder.